Think with me for a second. You are aging right now. While you watch this video, your cells are deteriorating. Your DNA is accumulating damage. Your telomeres are shortening. And the answer practically everyone would give for this is simple. It's time. Time passes, and we get older. It's the most obvious thing in the world. Wrong. Not slightly wrong. Fundamentally, profoundly, completely wrong. And Richard Feynman, one of the greatest physicists who ever lived, a Nobel laureate, the man who reshaped quantum mechanics, already had the answer. The physics he developed shows that time, at a fundamental level, has no preferred direction. Particles can travel to the past, and that's not a metaphor, it's the math. And aging isn't caused by time. It's caused by something else entirely. What you're about to understand will completely change the way you think about existence, aging, and what physics actually says about time. This model we have of time, the most intuitive one, the one that seems absolutely obvious, is exactly what physics is telling us is wrong. Let's start at the root of the problem, with the model we all inherited. Isaac Newton, in 1687, published Principia Mathematica. In this work, he built the mathematical framework that described the movement of planets, the falling of objects, the physics of the universe. And within this framework, Newton had a specific conception of time. Time is absolute. It is universal. It flows uniformly, independent of anything else, independent of matter, observers, speed, or gravity. Time simply exists, passing in the exact same way for the entire universe at the same time. Imagine a massive river, flowing in a single direction. Every point in the universe is inside this river. Planet Earth, the Sun, a star billions of light years away, all carried by the same current at the same pace. That is Newton's time, a cosmic entity that depends on nothing. It can't be sped up, it can't be slowed down, it can't be bent. And within this picture, aging makes perfect sense. You are in this river. The river flows. Over time, with the flow of the current, you accumulate years. Your cells wear out. Your biology gives way. Time literally wears you down. It's a direct, causal, inevitable relationship. This model was so powerful that it dominated physics for over 200 years. Not because physicists were naive, it was because it worked. Newton's equations predicted planetary motion with extraordinary precision. Newtonian physics built bridges, calculated projectile trajectories, and described almost everything we observe in our daily lives. Newton's absolute time wasn't just an intellectual hypothesis, it was the mathematical foundation of all physics. And this model fueled the intuition we all still carry. Time is responsible for aging. Time passes, and we decay. The Newtonian view was so unquestionable that biologists used clock vocabulary to describe life. The biological clock. The circadian rhythm. The organism as a machine being worn down by the friction of time. That metaphor was no accident. It was Newton. If time is absolute and universal, then aging is simply the cost of existing within the current of time. Inevitable. Irreversible. Natural. This paradigm was so deeply rooted that even Einstein had to fight to break it. And when he did, he revealed only the first crack. In 1905, Albert Einstein published the theory of special relativity, and what he did to time was devastating to the Newtonian view. Einstein showed that time is not absolute. It is not universal. The rate at which time passes depends on the observer's speed. The faster you move, the slower your time passes, relative to stationary observers. This isn't an optical illusion. It is a fact measured experimentally, with atomic clocks, with subatomic particles accelerated in a lab. The effect is real. But the part that completely destroyed Newton's time is what Einstein called the relativity of simultaneity. Two events that appear to happen at the same time to one observer might not happen at the same time to another observer in different motion. There is no universal now. There is no present moment that is the same for every point in the universe simultaneously. The now you are experiencing is local, personal, relative. The twin paradox makes this visceral. Imagine two twin brothers. One stays on Earth. The other boards a ship traveling near the speed of light for a long period and then returns. When the traveler comes back, He is younger than his brother who stayed. Not slightly younger, significantly younger. Years of difference depending on the speed and duration of the trip. Why? The intuitive answer would be, less time passed for him. And technically, that's correct. The clock on the ship ticked less time. But here's what that actually means. The thermodynamic processes in the traveler's body cell division, DNA damage, mitochondrial inefficiency, everything that makes up biological aging. All these processes ran slower. Not because time passed slower, in an abstract way, but because all physical processes, including biological ones, were affected by relativistic physics. The traveling twin didn't age less because less time passed, in the sense that Newton would understand. The twin aged less because they accumulated less thermodynamic disorder. And understanding why this is true will require us to go much deeper than Einstein did. What Einstein established is that time is not a single river. It's countless personal streams, each flowing at its own rate depending on local physical conditions. There is no universal cosmic clock stamping the same instant for everyone at the same time. But Einstein only showed that time was flexible. He didn't tell us what time actually is. Feynman did that, and the answer was much stranger than anything Einstein had suggested. Richard Feynman was different. Other physicists described the world in elegant mathematics and grand principles. Feynman just wanted to know, how does it actually work? He had a surgical instinct for the underlying mechanism. Around 1948, Feynman developed what we call the path integral formulation of quantum mechanics. To understand what this means, you need to forget the idea that a particle follows a single path from point A to point B. In classical quantum mechanics, Schrödinger's model, a particle is described by a wave function spreading through space. But Feynman went deeper. To calculate the probability of a particle going from A to B, you don't consider one path. You sum all possible paths simultaneously. All of them. The straight path, the curved path, the path that loops around the opposite side of the universe, the path that goes into the future and back to the past. This is not a theoretical daydream. It's the rigorous mathematical framework that works, that predicts experimental results with the highest precision ever achieved in any physical theory. And here's the thing. Paths that go backward in time aren't forbidden. They're necessary. They contribute to the calculation. Feynman's own mathematical formalism includes trajectories that travel back in time as an integral part of what happens when a particle goes from point A to point B. But the most explicit part comes from Feynman diagrams. Feynman created visual representations of particle interactions for quantum electrodynamics, the theory that describes how light and matter interact. In these representations, time is an axis. Particles have lines that move along this axis. And what happens with the positron, the electron's antiparticle, discovered in 1932, is revealing. In Feynman's formalism, a positron isn't just similar to an electron traveling backward in time. It's not a metaphor. It's not an analogy. It's the literal mechanism of the equations. In Feynman diagrams, you literally draw an electron with an arrow pointing to the past on the time axis, and that represents a positron. Think about what this means. Look at the PET scans used in cancer diagnosis. They work by injecting positrons into the human body. Look at the CERN detectors that routinely produce and capture antimatter. These are concrete, observable manifestations of Feynman's formalism in action. The antimatter that is produced, measured, and applied in medicine is mathematically described as matter traveling into the past. Backward time isn't science fiction. It's physics. It's the mathematical formalism that Feynman received the Nobel Prize in 1965 for developing. Quantum electrodynamics, or QED, the most precisely verified theory in the history of science. QED's predictions agree with experiments to more than 10 decimal places. It's the equivalent of measuring the distance between New York and Los Angeles with an accuracy of less than 1/10 of a millimeter. That's the theory. And in this theory, backward time isn't a mathematical curiosity. It's a necessary ingredient. If particles can travel to the past, if the equations work equally well forward or backward, why do we feel time only goes one direction? Why have you never seen a broken cup reassemble itself? Why have you never seen someone get younger? This is the deepest mystery in physics, and the answer will completely change how you understand aging. Here is the paradox in all its brutality. Take Newton's equations, the laws of motion. If you film billiard balls colliding and play the video in reverse, the physics seems completely valid. Balls separating, gaining speed, it's indistinguishable from a real collision. Take Maxwell's equations, electromagnetism, time symmetric. They work identically for the past and for the future. Take quantum mechanics, Schrödinger's equations, Feynman diagrams, time symmetric. Take Einstein's general relativity, the theory of gravity, time symmetric. Each fundamental theory of physics, the equations describing reality at the most basic level, works equally well forward or backward in time. Physically, there's nothing in the equations that prefers the future over the past. The universe of the fundamental equations doesn't have an arrow of time. There's a tiny exception, and it matters. The weak force responsible for radioactive decay violates time symmetry, but only extremely subtly. Physicists call it CP violation. But it's so small, so restricted to subatomic particles, that it doesn't explain the time asymmetry we actually experience. Billiard balls, fried eggs, aging, none of it involves the weak force. The asymmetry we live through is billions of times greater than CP violation could produce. So the problem remains. None of the fundamental laws governing your everyday world care about the direction of time. But you've never seen eggs unfry themselves as they're poured from a frying pan back into their shells. You've never seen smoke condense back into a cigarette. You've never seen memories spontaneously unlearn themselves. You've never seen anyone get younger as time goes by. Human experience is completely saturated with time asymmetry. Causes come before effects. You remember the past, not the future. Things break. They don't spontaneously assemble themselves. Systems go from organized to chaotic, not from chaotic to organized. This asymmetry doesn't come from the fundamental laws of physics. It doesn't come from the equations governing electrons, photons, and gravitational fields. It comes from something else. Something is creating the arrow of time that fundamental physics can't explain. And this something is exactly what will reveal the fundamental flaw in how we think about aging. Why is there a law that distinguishes past from future, if the fundamental equations don't? And what does this law have to do with the fact that you're aging right now? The second law of thermodynamics. Out of all the laws of physics, it's the only one that distinguishes the past from the future. The only one that points in a specific direction and says, it's this way. In isolated systems, entropy. The measure of disorder always increases or remains constant. It never spontaneously decreases. But what actually is entropy? Ludwig Boltzmann answered that in the late 1800s. Entropy isn't a force. It's not some cosmic law. It's probability. Imagine a box with 1,000 gas molecules concentrated in the left corner. You remove the divider. What happens? The molecules spread throughout the entire volume of the box. Why? Not because there's a law that says you must disperse, but because there are astronomically more possible configurations with the molecules spread out than concentrated in one spot. Disorder wins simply because it is the overwhelmingly more probable outcome. Boltzmann showed that entropy is a count of possible states. A high-entropy state has vastly more possible configurations than a low-entropy state. And a system evolving randomly will almost certainly end up in a high-entropy state, not because it's forced to, but because the space of possibilities is almost entirely made of high entropy. That explains the egg. There's no law forbidding a fried egg from reassembling itself into its shell. It's just that an intact egg is an infinitesimal fraction of all possible configurations. The probability of it happening spontaneously is so close to zero that it never does. Irreversibility isn't a prohibition, it's overwhelming probability. So here's the question. Why does the universe have an arrow of time if the laws are time symmetric? Because the universe started in a state of extremely low entropy. Sean Carroll and Roger Penrose have worked extensively on this. The Big Bang wasn't just high temperature and energy. It was extraordinary organization, minimal entropy. Since then, the universe has done exactly what probability predicts. Increased in disorder. Expanded into chaos. The arrow of time isn't a physical law. It's the entropy gradient. The universe started ordered and is becoming increasingly chaotic. The future is the direction of increasing entropy. The past is where there was more order. Feynman understood this perfectly. In his own lectures, he emphasized that the distinction between past and future comes entirely from the second law. Remove entropy, and there is no before or after in the fundamental equations. For Feynman, the deepest question in physics wasn't what are particles, it was, why is there a direction to time? And his conclusion was clear: the answer doesn't lie in the particles, it lies in statistics. The arrow of time isn't stitched into the physics of the universe. It emerges from the gradient between the low entropy initial state of the Big Bang and the high entropy future toward which everything is evolving. The past has less entropy. The future has more. And we are structures that exist within this gradient, moving always inevitably from the direction of greater order to that of greater disorder. And now that we know that entropy creates the arrow of time, what does this mean for aging? Forget what you believe about aging. It isn't time that wears you down. It never was. Look at what actually happens in your body over the years. You have approximately 37 trillion cells. Each one of them is a thermodynamic system, a machine that consumes energy, processes molecular information, performs chemical work, and produces waste. And each one is subject to the exact same law that governs the entire universe. Entropy increases. In every given moment, these 37 trillion systems are accumulating disorder. Aging isn't some mysterious biological clock. It's physics in action, on a cellular scale, day after day. Every time a cell divides, DNA gets replicated. The process isn't perfect. Mistakes happen. With each division, errors pile up. Some get repaired, others don't. Eventually, the burden gets too high and cells stop working. Mitochondria. Your cell's power plants are particularly vulnerable. They generate reactive oxygen species as a byproduct. These damage mitochondrial DNA, membranes, and proteins. Over time, mitochondria become less efficient. That's thermodynamics, not a biological clock. The proteins in your cells need to be folded into specific shapes to work. Heat, radiation, and chemical imbalances cause misfolding. Misfolded proteins accumulate and clump together. This is what causes Alzheimer's and Parkinson's. Molecular disorder. Entropy in action. Telomeres, the protective caps at the end of chromosomes, shorten with every cell division. When they get too short, the cell stops dividing. A cell that can't divide can't regenerate tissues. Senescent cells accumulate. That's a hallmark of aging. Thermodynamic degradation of information. Every single one of these processes, DNA damage, mitochondrial inefficiency, protein misfolding, telomere shortening, is a thermodynamic process. It's entropy increasing at the cellular and molecular level. Disorder accumulating in systems that desperately need order to function. Time doesn't cause any of this. Time is just the axis on which we measure these events. Time is the coordinate we use to label the entropy gradient. You age because entropy increases within the biological systems that make up your body. Not because time passes. The difference isn't just semantic, it's profound. Let's go back to the traveling twin. The twin who traveled near the speed of light didn't age less because less time passed. He aged less because his thermodynamic processes, cell division, DNA damage accumulation, mitochondrial inefficiency, all ran slower. Entropy accumulated more slowly in the physical system that was his body. Aging isn't damage caused by time. It's the accumulation of entropy. Time isn't the agent here. Entropy is. And that distinction changes everything. If we age because of time, there's nothing we can do. Time is unstoppable. But if we age because of entropy, because of disorder accumulating in biological systems, then the biology of aging shifts into a whole new domain. It becomes a problem of thermodynamics, not of the calendar. That's exactly what longevity researchers like David Sinclair are exploring. If aging is entropy and not time, then what exactly is this flow of time that we feel so vividly? Entropy explains why we age. But it doesn't explain why we feel like we're being carried along by a current that only moves in one direction. And the relativistic physics answer to that is perhaps the most unsettling thing we've seen so far. Einstein showed that space and time are not separate entities. They are aspects of a single structure, space-time. And this structure does not flow. It exists as a four-dimensional block in which all moments, past, present, and future, coexist simultaneously. It's called the block universe, or eternalism, the philosophical position that all moments in time are equally real. You exist right now, reading this. But you also exist equally real in every moment of your past, your birth, your childhood, yesterday, and equally real, your future, every moment yet to come. These moments didn't exist, then stop existing. They exist. In four-dimensional space-time, every event has fixed coordinates like a point on a map. The map doesn't move, it just is. The present isn't privileged in the universe. It's just where your consciousness is located in space-time right now. The flow of time, this feeling that moments pass, that the present becomes past, isn't physics. It's consciousness navigating the entropy gradient. Both Feynman and Einstein arrived at the same conclusion about the block universe. Einstein, in a letter after his friend Michel Besso died, called the distinction between past, present, and future a stubbornly persistent illusion. We don't flow through time. We're structures existing along a temporal dimension. Consciousness, which emerged from thermodynamically complex systems, processes information along this axis in the direction of increasing entropy. The flow of time is a construct of the mind. The past that feels like it's gone forever exists, locked in fixed coordinates within space-time. The future that hasn't arrived yet exists, in fixed coordinates that you simply haven't inhabited with your consciousness yet. Every moment of your life, every conversation, every joy, every loss, they all exist simultaneously along the temporal axis. Your consciousness exists along this axis and processes information sequentially, from lower to higher entropy. The vividness of the present isn't a property of the universe. It's a property of your consciousness navigating a gradient that has existed since the Big Bang. So, where does that leave us? Time doesn't wear you down. Entropy does. Time is a coordinate, like space. You don't say space wears you down just because you move through it. Time is the same, a dimension where events sit. What happens as you move along it is governed by the laws that operate there. And the law governing aging is the second law, not time passing. This changes the questions. Not how to stop time. Time's not the culprit. But how to keep biological systems in low entropy states. How to boost cellular repair. How to slow molecular damage. And the most mind-bending conclusion? In the block universe, all moments coexist. You, right now, exist in fixed space-time coordinates. So do all the other moments of your life. The past left behind hasn't disappeared, it exists, at its coordinates. The feeling that it's gone is a consciousness thing, processing information along the entropy gradient. At the most fundamental level physics can describe. You're a structure existing along 4 dimensions, 3 spatial, 1 temporal. Consciousness, being alive, is processing information along the temporal axis in the direction probability indicates. It's not simple, but it's far truer than what intuition suggests. And it's not just theory. Atomic clocks on GPS satellites need relativity corrections to work. The decay of muons in particle accelerators confirms time dilation. CERN's antimatter is mathematically matter traveling backward in time. These aren't thought experiments, they're real, measured phenomena. Subscribe. The next video goes deeper into this weirdness, and physics gets even stranger from here.